We now present M3ashy multimodal material synthesis via hyperdiffusion. M3ashy enables high-quality generation of complex real-world materials by leveraging neural fields as a compact continuous representation of BRDFs with condition of different modalities. In addition to multimodality synthesis, two new material datasets, a novel statistics-based constrained synthesis, two BRDF distributional evaluation metrics and ablation studies are introduced or conducted. High-quality material synthesis is essential for replicating complex surface properties to create realistic scenes. The bidirectional reflectance distribution functions, BRDFs, describes the relationship between the incident and outgoing radiances for a specific material, which are used in the rendering equations. Despite advances in the analytic material appearance generation, the synthesis of real-world measured BRDFs remains largely unexplored. We adopt MERL, which is a data-driven BRDF dataset. It assumes isotropic and spatially identical material for simplicity. Our material synthesis framework starts with AugmentMERL, where we expand material data using RGB permutation and PCA interpolation on MERL dataset. Next, we fit neural fields to individual materials, creating neural representations of their appearance, forming new MERL dataset. Then, a hyperdiffusion model is trained on new MERL dataset for conditional material synthesis, guided by type, text, or reference images. Finally, statistics-based constrained synthesis ensures materials match the desired type. Together, these steps enable flexible, controllable material generation. All baseline models fail to capture the underlying distribution effectively, resulting in meaningless samples with severe artifacts in the synthesized materials. In contrast, M3ashy successfully captures the complex neural material distribution, achieving significantly better fidelity and diversity. Our materials also support spatially varying rendering configurations. Diverse and high-quality rendering results are presented here using our synthesized neural materials. The evaluation mainly focuses on the fidelity and diversity of the synthesized materials, which is still an open problem in this field. To fill in the gap, we raise the idea of utilizing minimum matching distance, coverage and one nearest neighbor with either the image quality metric or the BRDF distribution as underlying distance function. Please refer to our paper about the details of the BRDF distributional metrics. We demonstrate the effectiveness of M3ashy through extensive experiments, including on this brand new series of metrics. We demonstrate the conditional synthesis capabilities of M3ashy across various modalities of input, material type, text description, or material images. M3ashy synthesizes materials aligning with the conditions and generalizes to unseen input labels. Based on the statistically properties of data-driven materials, we classify materials into 7 categories based on their reflective properties, including diffuse, metallic, low specular, medium specular, high specular, plastic, and mirror, via a novel constrained synthesis over the unconditionally synthesized samples, without deep learning. We conduct sparse BRDF reconstruction and BRDF compression experiments following hypernetworks for generalizable BRDF estimation. The results in the table demonstrate that training on AugmentMERL consistently enhances material quality across all evaluated metrics, further validating the effectiveness of our augmented dataset. Our key contributions are as follows. First, we introduce two new material datasets, AugmentMERL and NewMERL. Second, we enable multimodal synthesis of data-driven material appearance models. Third, we propose a novel statistics-based constrained synthesis method. Fourth, we present two BRDF distributional evaluation metrics for quantitative analysis. And finally, we conduct comprehensive ablation studies to validate our framework. Promising directions for future work include developing physically accurate neural representations of BRDFs, extending our framework to handle more complex and diverse materials, and performing a detailed statistical evaluation of our multimodal synthesis results. Many thanks for listening. We'd be delighted to hear your feedback or see any future work inspired by M3ashy, multimodal material synthesis via hyperdiffusion.